Oh, actually, it might be here. Let's go back to PowerPoint, or let's go, yeah. I might be able to open it. If I go to the working version. Am I gonna get?
You're always super cute.
Oh, box does not show up.
Oh man.
Nor does my disk now. I might have ejected that. Let's go to PowerPoint and let's exit that and let's open a different
Do you have your earbuds?
box. Yeah, there
I can go get them.
I should put an alias. I will put an alias on the top here, so we don't have to do this every time. Hello, go there, go there. Let's see if it showed up there. No, best thing to do is just go grab it. Nope. Goodness gracious, can you be any more annoying? Okay, oh, damn, I should have shut that. Ugh. Oh, man. Okay, at least we have that.
What are the sections? It should be in box, PowerPoint lectures, and then week 2. Or sorry, not week 2. Is it lecture 07? Yes, lecture 07. This one is. Is it not showing? I think it's not. Yeah. Oh. Not really sure. It's no, it's definitely not six. Do you know where you put this lecture? Because this one is specifically 06 or 07.
Yeah, you want to get it from box?
Yeah.
I'm going to going 07. Ready for upload 07. Yeah, start. I think I'm going to start here.
Got it.
Because that has 6 and 7.
Got it. That's what I thought.
Together. So I need to join.
Yeah.
What is that? I guess I could go join the other way.
Ready? 924
924
51 60 21 95.
That has a password. Go Bears,
Go
I think.
Bears.
Oops. The letter O, right?
Yeah. The only password we use in this class.
What does that say? Call me using internet audio. I don't want to call. I want to.
It's correct.
Yeah.
You want internet audio?
I do. I don't want to hear anything. Why am I not mute my output audio? How do I? Yeah. Can you output your output audio? You should be able to do that.
It's like very challenging to do on iPads. Nope, that's all.
I will just. Come on, baby. So will I can go?
Yeah, I think so. I don't know.
You can exit out of all of it, but then you can
Yeah, that's okay. So I need to be attached over here.
This one's good. Alright, looking good. Awesome. Battery's
Test
good.
that. Test audio. Test test.
I think that's
Click on. And that is this fan on. Okay. Barely enough time.
We made it.
8. Morning, everyone. I think the live stream is live and everybody's with us. Couple announcements before we get started. We have an exam a week from today, right? Monday, 6 p.m., 6 to 7:30 p.m. That'll be delivered exclusively online, and it will be delivered through B courses. It'll be essentially a B courses assignment. You'll get in there and start it. It will become available at 6 p.m. and it will cease to be available at 7:30 p.m. You'll have those to look at it. We may shorten that to just 1 hour and shorten the exam, simply to give, first exam needs to be a break, and I know this has been a rush to catch up, so first exam will make a little easier and probably just go for an hour. It'll be all multiple choice. The second thing is Prism will be launched this week. So tomorrow we'll give you a little tutorial on how to use that. But your assignments in e-courses will start taking you to the Prism software. And the Prism software is brand new software that we're developing. Like I said, we'll give you a tutorial on it tomorrow so you can understand how to use it. And it will jump back and forth from e-courses to the software automatically. And you'll have to do an initialization. You'll have to go to B-courses, start an assignment, then log in and register with your activation code at the Prism website. And once you're done with that, it should maintain the connection between those two pieces of software for the rest of the semester. Want to say something about attendance. Attendance credits are possible to get for this course. Read the course info page, especially before you send any emails to the staff about how that works. If you send an email to the staff about how it works, the staff is going to be upset. You don't want to upset the staff. So read online how everything works. There's also, there'll be user guides about how to use the Prism software and things like that. So I think that was it. Was there anything else we wanted to mention this morning?
There will be an alternate exam time. Unclear when that'll be.
There'll be an alternate for DSP?
DSP and or time zone.
Yeah, okay, so time zones. There'll be an alternate exam time for people on other continents. The DSP students will always get time and a half, and we'll just enter you guys specially, so your time just goes time and a half. Okay, so we were talking about diffraction and interference. These are two separate things, for instance, diffraction and interference. Diffraction is the general diffraction, the general spreading of a beam when it goes through a slit, and we saw that last time. I can overlay it here, so there's a overall diffraction envelope over here that's making this peak big and these peaks smaller as you go out. So that's due to the edge effects of the slits. And so that's just dispersion that occurs. Then there's the idea of the waves passing through and then interfering with each other. And we said there's two kinds of interference: constructive interference and constructive interference, to remind you, is when one waveform adds to another waveform and they're in phase. We say that their peaks and troughs come at the same time. That's called in phase. And these add to give one bigger amplitude wave. So the peaks add and the troughs add to give you a bigger amplitude wave. So you can also have destructive interference. And destructive interference, I'm going to draw over here where there's a little more room. Destructive interference is when a waveform comes in and a waveform adds to it that is out of phase. So now peaks and troughs overlap, and you get a sum that where there's no intensity. And that's what you're seeing here. You're seeing constructive interference, then destructive interference, and constructive interference, and destructive interference. And this tells you that's a unique wave-like behavior. And that wave-like behavior, once passing through the slits, has wave-like properties. We can look at it in a simulation online. There's a lot of them. This one will take a second to load, I think, but it's fun to look at, of course. So we will turn off a few of these things. So what you have here is an illustration of the waves passing through two slits, a slit here and a slit here. And you can see we've drawn wave fronts now. So these lines are the peaks and troughs of the waves. And it's coming from two sources, two slits. And you can see what happens is as the waveform passes and goes through the two slits, what you start getting is areas where the waveforms add to give you a higher intensity, and where the waveforms subtract destructive interference to give you less. So I will take away my annotations and let's see if we can let that go. So here are the waveforms propagating, and you can see as they propagate, there's areas, we'll pause that a second, there's areas, I believe I can show them, there's areas of, oops, I gotta get my pen here. Those don't show up that well. So let me see if I can show them. There's these dotted lines here going through and showing you where those waveforms are constructively interfering. So you would get a peak here where those guys are constructively interfering, and you would be overlapped, a diffraction envelope overlapped on top of that. So the reason this peak isn't the same height as this peak is that diffraction envelope. Okay, so it's kind of fun to watch that pass through there. So I think I can restart the animation, and you can see the wavefronts. And I believe we can show the interference pattern. So there you can see the intensity of the interference pattern, and you have a strong constructive, oops, you got to go back to my pen. And I'll use a blue pen because that's kind of what's going on here. So you have strong constructive interference here, and then weaker constructive interference as you move out. So you have destructive, constructive, constructive, destructive, constructive, destructive. You can see the bright areas. Let me get rid of the wavefronts, because they're overlapping there, if I can. Let's reset here and reanimate if we can. So there you can see, that's actually not a very, oh my God, that's not a very pleasing picture of bright and dark spots. So this is dark, oh no, okay. So you can see, I don't know how much this is showing up online, but there's dark and this bright blue, bright, dark, bright, dark, bright. So you do have dark to bright to dark to bright to dark to bright to dark, bright, dark, bright, dark. Is, well, a wave that has to go from, let's go from this slit, a wave that has to go from this slit to that point there travels a different distance than that wave. So they have their wave fronts. Now I have to be a great artist. But by the time they get to here, they're the same wavelengths. But since this one had to travel farther, by the time they get to here, they are in phase. By the time they get to the dark areas, this one has traveled just a little farther, so they're out of phase and give you destructive interference. So let's go back to our PowerPoint, and we can do a chem quiz on that. Oh, I will mention, we talked about this a little last time. The intensity here is proportional to the probability, that is the likelihood that light beams are striking in that region. That's a rough association, but intensity is proportional to the amplitude squared, as you know, and so high amplitude, high probability, lower amplitude, lower probabilities as you go out. This sign here, this little squiggle, that's I'm using that for proportional, or goes as, the intensity goes as the square of the amplitude. You might have seen the symbol proportional that looks like that. It just means that these two are within a constant of each other. So I equals some constant times a squared. If we get rid of the constant, it's just I is proportional to a squared, the amplitude. So let's do a chem quiz on that. How will the two-slit interference pattern change as you increase lambda? So I'm going to increase the wavelength. So I've even drawn it here. I've gone a green wavelength here, red, longer wavelength. How will the interference pattern look after I change the frequency, the wavelength of the laser going through those two slits? So think about that for a second. When the poll is begun, I think it has. I think I can go. Oops, I can't do that. I thought I had the group of 4 pasted in between there. I don't. Are we set up with source change? Are you ready? Tell me. Okay. Our second source. We'll put up the group of 4 here, as we tend to do, to see if that helps you with your explanation. So think about that for a second, and we'll take a vote. So it looks like a lot of you already have an idea just after kind of a minute of considering it. So let's just take a few seconds here. If you haven't responded, go ahead and respond. And Ryan will show us what you're thinking. Go ahead, Ryan. So C is pretty popular, and more popular than A and B. So let's talk about that for a second. Ryan will start the poll again. Ryan, do you need me to display the other slide, or can you?
If you can just, well, you can walk me out of it.
That's okay. You're good.
No, I have to do the other one. It's
Okay. I'll drop into a breakout room and chat. I'm gonna leave this room. Oh. Okay, so we've had a few minutes to talk about that. Let's see what you're thinking. Let's give you guys a second to vote. There's about 88 of you. If you haven't voted yet, go ahead and push a button so we get a good distribution. All right, Ryan, let's see what that group is thinking. So now there's a lot of people thinking C. So you're thinking longer wavelength coming in, kind of gives you a longer wavelength picture here on C. So let's go through that. Am I on source 2 here?
Yes. Just go to recent apps.
Yeah, that's a better idea. But I don't know which one of those buttons is going to get me back. So here we are. So let's recall kind of what's happening. So here you have light going through 2 slits. If they meet in the middle, those waves have traveled the same distance. So those waves traveling the same distance are going to be in phase. They started in phase here because it was a laser. We'll talk about, maybe we'll have a chance to talk about that. But laser light is coherent. It's all in phase. So these guys are in phase because the light beams travel the same distance. As you go to a spot here, then this travels farther. And what you want it to do is you need to go, to get to your next maxima, you have to start traveling a wavelength farther. So this distance here corresponds to the fact that this path got longer by a wavelength. So, indeed, larger spacing because lambda got longer. So, I agree with the C people. That's fantastic. I think we'll do this quickly. Let's just do this one where we talk right away. You don't have to do two. I want to do this one because this is interesting. A lot of people are interested in this phenomena in general. So this is scattering. So rather than looking at an absorption, we're looking at something similar. Light's going to pass through this medium. In fact, we really haven't even had any medium so far. Everything we've done so far could have been in a vacuum. Light travels in a vacuum. Electromagnetic radiation travels in a vacuum. But if it goes through a medium, it'll interact with the medium. And one of the things that'll happen is some light is scattered and some light is not scattered as much. And I've plotted the relative intensity of the scattering. So wavelengths here more scattered than wavelengths here. So talk about that for a second. What is the predominant colors of the light coming out at the high scattering angle? So at position 1. Let's talk about that for a minute and see what you think. Can I join a breakout room and chat? You can mute me.
You were unmuted. Start again.
Okay, sorry, I've been muted apparently the entire time. So let's start again quickly.
Sorry.
We have high scattering angles for the bluish colors, low scattering angles for the reddish colors. So when the blue light passes through this medium could be the atmosphere, it is scattered better than the reds. So the reds are passing through. And here you'd see blue, more bluish. And this is why the sky is blue. That's why I wanted to go through this. You're out of Chem 1, you're at Berkeley, people will ask you, why is the sky blue? Because you're looking up at the sky, white light is coming from the sun, blue is being scattered every which direction, so it's coming at you from all different directions. And if you look over here and over here and over here and over here, you'll see the blue being scattered at you. And blue photons are scattered all through the atmosphere, randomly come to you, other wavelengths pass right through. It's also the reason sunsets appear orange-ish or reddish, because as you look at the horizon and the sun, you're looking at the direct path of the sun. So you see these wavelengths, direct path of light. And the more particles in the atmosphere, the higher this scattering, and the more blues are scattered away. So at sunset, there's a lot of particles in the air, it'll look even redder. The question?
So why isn't the sky purple?
Why isn't the sky purple? It's a combination of a lot of blues, and the combination of these blues give you bluish. And when you start going too far this way, you're starting to get into ultraviolet, and we can't see those. So the question is, how blue? Well, that's just the blue. That's the combination we just happen to see. So we'll pass through this. Highly scattered blue is what you see. This one would have just told you why sunsets are red. So let's go on. We talked about the wave nature of light, and we understand now quite well that the light acts like a wave. We've kind of proved it because we've seen the interference pattern, constructive and destructive interference, which is manifestly wave-like. I love when somebody says something like manifestly wave-like. That means it's a property of something that is a wave, and it's not a property of something that's not a wave. Manifestly wave-like. So we've seen the entire electromagnetic spectrum. Here I just show the visible region again. So this is the region from 400 to 700 nanometers. And you should be roughly familiar with the fact that the visible portion of the electromagnetic spectrum goes from 400 to 700 nanometers, and the 700 nanometer wavelengths are reddish, and the 400 are bluish. On the exam, we might just assume that you know the approximate wavelength ranges. We're not going to ask you for specific, but you should know about what they are. So here I've drawn some colors. Blue, and remember, the blue are the high frequency or high energy. The orange are down here at the other end, longer wavelength, lower frequency. Medium wavelength here, I've done yellowish, and I've also drawn it at higher intensity. So higher peak to peak amplitude. So this is the amplitude, and intensity goes as the amplitude squared. So the amplitude squared, did I even do yellow? More colors, more colors. What is that one? No. I would like to draw in yellow. Oh wait, how about a double click? No. I can't get yellow, so screw that. I will just draw in the same, well, no, this is a different color. Blue, unfortunately. So the amplitude goes as the square of the wavelength. So the square of the wavelength looks like that because this is a negative wave. This is below the axis. This is above the axis. So this is essentially there's all plus signs here and there's all minus signs here. But when you square it, those all become positive. So one reason the intensity is proportional to the square of the amplitude. The probability proportional to the square of the amplitude. There's no probability involved here, but when we were back at the diffraction and interference pattern, we had the probability proportional to the square of the amplitude. So we have, again, whoopsie. Oh, that's all we're going to see. I've just reminded you, the wavelength times the frequency is the speed. And for electromagnetic radiation, that speed is the speed of light. We can have waves at all kinds of speeds. So water waves or sound waves, they travel at different speeds. But when we're talking about electromagnetic radiation, that goes at the speed of light. So let's talk about filtering it. So let's say light passes through a filter, and that filter reduces the intensity by a factor of 2. What would happen if the light passed through a second filter? So think about that for a second. What would the intensity be as you've gone through 2 identical filters? And Ryan will start the quiz, and hopefully, yes, I've put the group of 4 here. But Ryan, you can also get it, but you don't have to get it right this second. Here's the group of 4. Think about that for a second. I put these up so you have some of the information you need. This one you'll talk about on your own. Just for a minute. Are you ready with group of 4?
No, it's set up to do before.
Yeah, usually when we show them the distribution, we show them the group of 4. Okay. And for your convenience too, I put the groups of 4 in between all of them. Okay. We've already got about 100 of you already, so let's see what you're thinking. Ryan will show us the distribution. Oh my goodness. A lot of people are just saying A. So let's look at that. You are saying that when I go through a second filter, I also drop it by a factor of 2. And I agree with you. If you drop by a factor of 2 again, you're 1/4 the original intensity. So I want to look at doing that in more steps. So let's say you took a monochromatic light. And when I say monochromatic, I mean 1 wavelength. Monochrome, 1 color. I've just drawn it as a flashlight, not normally monochromatic, but let's say it's a laser, a fancy flashlight. If I filters in, I keep, and standing here, as each filter goes in, the light just appears to be dimmer and dimmer with each filter that goes in. So the question is, as I keep dimming the light, the monochromatic light, what happens? And this is a very interesting phenomenon. As you keep dimming, the light goes from a continuous glow. If you have your filters calibrated exactly right, you'll start to see flashes of light. Now this you can actually detect with your eyes. So if you're in a very dark room and you do this, your eyes are totally dilated, do it in a very dark room, and you increase the filtering, you'll begin to see flashes of light. So the light goes from continuous glow to individual flashes. Now, individual flashes sounds more like a particle, beep, 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 than a wave. So indeed, there is some particulate nature to light. We call these particles of light photons. Now we have to be careful. It's a particle, but it's something that acts like a particle. So light is acting like a wave. We're acting like a particle here because it's discrete. There's little packages, not continuous anymore. We have to be careful because they're particles that don't have any mass. So it's not a particle in the true sense of physical particles like BBs or nuclei of atoms, but they have a distinct energy, and it's equal to Planck's constant h times the frequency. Planck's constant we haven't seen yet. Here it is, an incredibly small number, 10 to the minus 34, and then there's these crazy units here, meter squared kilograms per second. We'll talk about those units a little more a little later, but an incredibly small number. So these particles are unbelievably small. The packets of energy are the frequency times that incredibly small number. So our packages of light, our particles of light, are extremely small in energy. So let's go back and put that on our plot here. So now we have light. So we have the wave-like nature of light in the first equation. The wavelength times the frequency is the speed. Now we have the particulate nature of light, the energy of the photons below that. So we've separated light into photons. What about that electromagnetic radiation? So we talked about the picture of electromagnetic radiation as oscillating electric fields, oscillating forces, influences on particles. So oscillating charge, these guys, these electromagnetic waves can have influence on particles in at a distance. If your light is traveling, it can have influence on that particle. And it has influence on that particle by starting to move it. It can give it a kinetic energy. So our oscillating fields in our electromagnetic radiation can give real particles, I showed you an electron there, they can give them a kinetic energy. They can start them moving. In general, they bring them to a high kinetic energy and then low, high potential, high kinetic energy, low, and go back and forth. So this brings us to an interesting question then. The particulate nature of light, can we look at it? So this is a metal surface, and we're going to let light shine on it. So we can let light shine on it, and it turns out if you let light shine on it, it can actually eject electrons. I think we understand why. The electromagnetic field can get those electrons moving, and it can push them, get them moving so fast, they leave the metal altogether. These are called photoelectrons. They're ejected from the metal. So they start traveling in space freely, and you can detect them. A beam of electrons leaving the metal. So there's a photoelectron flying off the metal, and it's frequency dependent, it turns out. the different wavelengths give different kinetic energies. Now, that is an interesting phenomenon. When physicists first saw this experiment, and I can show you Lonnie doing that experiment. So Lonnie in the laboratory, hopefully this is photoelectric effect. So here he's going to do the photoelectric effect, and I want to go.
Electrons emitted are shown on the meter at right. If he puts a red filter
and I
in
want
the
to
path,
mute.
now only red photons can escape the metal, and you can see they do not have sufficient energy to eject photoelectrons.
I really want to play this without the volume. I guess I could just mute the entire screen. That's where the volume's coming from. It's hard. Pressing buttons here makes. I want to get to big screen, but tapping anywhere on mute. So what Lonnie's done here is he's put two colors now of filters in the path of white light. So he put a red filter in the path of white light, and he didn't get any photoelectrons. So here we have the photoelectrons being displayed. So let's see what's going on here. We have white light coming through this grating that breaks it up into the various colors of light. And then Lonnie put a red filter in the path. And when he put a red filter here in the path, we got no deflection on this meter. We didn't detect any photoelectrons. We didn't detect any electronic current at that source. Then he's going to go up to yellow light. So let's see if we can have him keep going. And now he's going to go to green. He passed by yellow and he's going to go to green. So we'll see if we can see that. So there we have. Now we have some, I said pause these. Now we had some intensity of photoelectrons coming through. So we saw that dial deflect, and we'll continue doing that. Now he'll put blue in, so now higher frequencies are being allowed through, and we have even higher electron energy coming out. So more kinetic energy of the electrons coming out. So there's another feature to this, and that is if you increase the brightness, the intensity of the radiation down at these low frequencies, longer wavelengths, that does not push out more electrons. That is, if you shine red light on, so you got your red laser and no electrons are coming out, if you crank up the intensity, get it very bright, you'd expect, well, maybe shouldn't I get some electrons? The answer is you don't. And this had physicists confused. So what was going on? If you imagine I have a sheet here and a ping pong ball. Sheet's attached to the wall and a ping pong ball. I want to throw the ping pong ball off the sheet, electron leaving a metal. So the question is, if I'm doing this at some frequency, putting in some wavelength, and the electron is not leaving the sheet, how do you think I should get it to leave? Well, you would think, do this. Increase the amplitude, increase the brightness, and pop that thing off of there. But that doesn't work. And physicists were confused by this for years. And it seemed reasonable. More intensity, why don't you get the electron to leave? And the answer is, and Einstein was the person who solved this. He applied the particulate nature of light. He didn't discover the particulate nature of light. Max Planck, who the Planck's constant is named for, he discovered these discrete energy packages. And Einstein applied that discrete energy package to this problem and it explained it. In fact, Einstein won the Nobel Prize for that. Everybody associates Einstein with special relativity and relativity. He did not win the Nobel Prize for that. He won his Nobel Prize for explaining the photoelectric effect. So here's the idea. Actually, you may not know this. The story's kind of interesting. Max Planck and Einstein, they used to go to the junkyard together. And they used to break windows of the cars by throwing rocks at them. And Einstein, one day, a clever guy, he invents this little pea shooter where he can shoot peas really fast through his pea shooter and make them strike the windows of the cars. But what he noticed is, no matter how fast he shot those peas, it didn't break the window. So as he increased the intensity of his spray, it didn't break the window. And Max Planck was sitting there and he goes, well, of course you didn't. He just grabs a big rock and he throws it at it and it breaks the window. So Einstein's going, why doesn't that happen? Well, I understand that. The bigger rock, it carries more energy in its momentum than my little ones. So if one of my little ones doesn't have enough energy to break the glass, 1,000 little ones aren't going to break it either in rapid succession. But one big one would break the glass. And Einstein sees this and he goes to Max, he says, oh yeah, you said that the particle nature of the light, the E times the HU, the bigger particle and the little particle. And he's so excited, oh my God, I think I get it. And he's excited because he's going, oh, Nobel Prize, oh my goodness. Oh, I think I peed it. I'm so excited. So Einstein runs back and he writes this down, and it turns out it does solve this problem. Do I have a demo?
There are a bunch of questions.
Oh, there's all kinds of questions coming in. Okay, go ahead.
The more electrons you remove from the metal, oh no, that's not the one. Sorry. Where'd it go?
The electrons leave, won't the metal eventually run out of electrons? LMFAO.
Okay, so the question is, if you're pushing electrons out, won't the metal eventually run out of electrons? And yes, you could imagine that being the case, but you're actually knocking out relatively small amounts of electrons. We'll learn that the numbers of electrons in the metal are just ginormous, and it can afford to lose some of them, and it eventually will change in charge. The surface will charge. Actually, electrons distribute themselves a little better and mask that charge change to a great. So you go to electron deficit. Good question. Does the electron deficit change to a great? So you go to electron deficit. Good question. Does the electron deficit cause the metal to get very positive? The answer is it would take a long time for that to happen. So good question. Was there another question?
Yes. How does increasing the amplitude affect the electrons emitted then? Rather than having more electrons emitted, are they emitted at a faster rate?
So that's a good question. So the question is, well, then how does the amplitude affect it? How does the intensity affect it? And do you get electrons coming out at a faster rate, more electrons per second, more current passing through your detector? And the answer is absolutely yes. And why is that? Well, that's because higher amplitude, more intensity, is a measure of the number of photons per second traveling in the wave. Why is light more intense? Bright, because more photons per second are hitting your eyes. Brightness and photons per second correlate with each other. So intensity, amplitude, corresponds to more particles. And we've seen that already. We said, well, higher probability of striking something is higher amplitude, or particles per second. Great question. I think I have a quick demo about this. Oh, that's Lonnie again. So let's go back to my PowerPoint. That one, maybe? That one, maybe? So here's a little picture of the experiment happening. So we'll let that run. That has to load up. Give that a second. Hopefully it's not too long to load up. While it's loading up, I will just tell you. So the more photons per second, the more electrons. They don't have higher kinetic energy. They have more of them, more intense. I should have started these in advance. I was trying to start these in advance so they would just start up, but the screen wasn't cooperating. I'm not going to wait for this to, okay, there it goes. Go, baby. Give us a picture.
Remember, you have to say nice words to it.
I said go, baby. That's pretty nice. Okay, Photoelectric Effect is starting up. I will try to start these a little faster because we're actually way behind. This is taking too long, and we are way behind. We can look at that another time. Basically, it's just an animation showing you. Oh no. Now I'm terrified because.
I need to do an idea of it for me.
Let me see if I can just start it again. Should be able to. Don't drag on me. So we understand now what's going on in broad strokes. And I'm taking too much time on this. I have to pace ourselves a little faster. So we have electrons coming in. And now we know higher frequency ejects electrons. And higher frequency ejects electrons individually at a higher kinetic energy. And then when I go to higher intensity, it's more electrons, but still at the same kinetic energy. So you can think of it like this. You can think of the electrons trapped in a well, and the energy of the photon, the red ones, aren't enough to get out of the well. As you increase the energy of the photons, you get enough energy to escape the well, and you'll get more kinetic energy. You can plot the kinetic versus the frequency. So I'm going from reds to blues along here, and electrons start coming out, and as I go to higher frequencies, I get more kinetic energy. So we can write that down mathematically. There's a couple different metals now. So green light is ejecting an electron here. Different metal, metal 2, you have to go up to blue light. So this potential well is different for different metals. And you can write it down. The kinetic energy is the energy of the photon minus the amount of energy of the well. So it's pretty straightforward. So let's do it again. Let's just talk about it. So shining a beam of light on, so that's pretty straightforward. So let's do it again. Let's just talk about it. So shining a beam of light on a certain metal has no effect. What change would eject electrons? And we'll go right to talking about this one because I think you have an idea of what's going on. I will bring back the group of four via, well, I can just do it.
Nope, do it for me.
I can just do it here. So here's the group of four. Talk about that. Just talk about this one amongst yourselves. We won't do a double vote on this one. Think about this for just a minute. I think you'll know the answer to this one. So, Ryan, when you're ready, register to vote. Think about it for a minute. Powerful person and influential, but you cannot mute every breakout room. So let's see what they're thinking with 96 responses, Ryan. Most of us are thinking C. Let's see what I think. Oops, I don't want to do that. That will really mess us up. So more photon energy is needed. If one wavelength didn't do it, what do I have to do? I have to go to higher energy photons. Higher energy is shorter wavelengths. So the question is, do I increase the intensity? Do I decrease the wavelength or increase the energy? A lot of people were saying increase the energy. That's absolutely right. Increasing the intensity will not do it. If one photon doesn't do it, a million aren't going to do it. You have to go to a higher energy photon. So yes, that's true, that energy increases, but energy will increase if you decrease the wavelength. So you could have said B or C, and you would have been correct there. So here's a combination of metal and photon. So think about this for a minute on your own. So we are going to take two different metals, and I've done the two metals, 1 and 2. Here are the intensities of the electromagnetic spectrum going to higher frequency. And the question is, which combination of photon and metal ejects an electron with the highest kinetic energy? So you have pairs here. Yellow photon on metal 1, green wavelengths on metal 1, or blue wavelengths on metal 2. Think about that for a second. On your own, we'll have Ryan start the poll. Before Ryan. Are we ready? Before Ryan. Mm-hmm. Well, let's see what you're thinking. I'm probably rushing you a little bit, but let's see what you're thinking. Push your button if you have not so far. And remember, don't panic about pushing your button. You do get attendance for pushing your button, but we're very generous. You can miss a lot of button pushes. Ryan, let's see what people are thinking. B and C, both popular. Let's talk about that as a group. If you could put me in a group. And I could have my audio back.
You're back.
I guess there's quite a bit of lag. Okay, I'm back. There's a little bit of lag, I hear, in the live stream. But Ryan, if you could show us what people were thinking after a discussion. Oh, B and C still equally popular. That's really interesting after that discussion. A, not very popular. So let's see if we can think about that for a second. I'm going to go back to my version of the PowerPoint. Let me try that again. Go back to my version of the PowerPoint. Oh, maybe I am. I did. Okay. So we have 3 different photons, 2 different metals. So the question is yellow, green, blue. That's increasing in frequency. So the yellow lights in general have lower frequency than the greens. You go from yellow and turn into green and then turn into blues. So the biggest frequency a yellow can be has to be less than the green. So if yellow strikes metal 1, you can read the kinetic energy. If a green photon strikes metal 1, you can read off the kinetic energy. So that's high. So far we have B, but blue has higher frequency altogether, but blue is striking a metal that holds on to the electrons more tightly. This here is the first frequency that can eject a metal, eject electron from metal 2. Here's the first frequency that can eject from metal 1. So you have to put in all this energy just to get an electron to move off the metal, and then energies beyond that will give it more kinetic energy. So more tightly bound electrons in metal 2, so a lower kinetic energy, even though you had a higher energy photon. So we'll summarize here. White light works like a wave. We know that E equals h nu and hc over lambda. So I've used lambda as well as the frequency to get the energy. H is here 10 to the minus 34th. I've written joules seconds now, which is a more common unit for our purposes. But it also has some particulate properties, and that's related to the momentum. But momentum is mass times velocity. So we're kind of at an impasse here because the photons have no mass. So how can they have a momentum? Well, it turns out they can, and I won't go through this in much detail. But if you look at a relativistic mass, so this mass, I've done a little m star for the mass of the photon, times the velocity. So the velocity is the speed of light. So you have this expression for the momentum. That means you can take this relativistic mass. This is Einstein's famous relativistic mass equation, mc squared. I know you're excited. You're excited now because you're using E equals mc squared, and that's what you thought you would do when you got to Berkeley. I can recast that then. I can put the momentum, since it's equal to m times c, in the expression. But I can set the energy also equal to hc over lambda, because it's all energy. So the mass goes away in the on the face of it, and I talk about just the momentum and the speed and wavelength, but the speed cancels out, and I can write the momentum in terms of just the wavelength and not a mass. Yay! So I have a particulate property, momentum, in terms of a wavelength property. So we really have unified the two here. This particulate property, momentum, is Planck's constant divided by the wavelength. We can write that in terms of the wavelength. But the wave-like property, then, we should be able to cast in terms of the momentum. And that's just rearranging that expression. So light and particulate properties together, we have this crazy duality of light and particles. It's not something that you would think of. They're two different things. It's like, it's a floor polish and a dessert topping. You wouldn't expect to have both those properties come together. But here we have two disparate, separate properties in the same phenomenon, light, and we can cast the particulate nature and the wave-like nature in terms of the momentum. So let's look at this. I'm going to split photons now. So I'm going to take a photon at 400 nanometers and go through this splitting film that literally divides the photon energy up. And it'll divide the photon energy up between two new photons, one of them at 1200 nanometers. The question is, what's the other wavelength? So let's discuss that one. Go ahead, discuss that one together. We won't do 2 votes. We'll do 1 vote on this one. So if you could add me to a breakout room, Melissa.
Okay.
So let's see what you're thinking. after some discussion there. 104 votes. My goodness, this is the most spread out we've ever been in a chem quiz. No consensus either way, even after discussing it. So let me give you my thinking on this. So we have this idea that a photon at 400 nanometers comes in. That's a high-ish energy. And we split it into two new ones. Now, splitting into two new ones, we can't get any more energy. So the energy of the 400 nanometer is split into two lower energies that have to add to that 400 energy photon. So got to conserve energy. And that's interesting. That's easy to do with a photon. It acts like a particle, but I can divide it up pretty easily. If this were an electron that is a particle, I couldn't break that apart. But I can divide the energy of photons. So our idea then is, well, these two have to add in energy to the 400. There's a 1200, that's lower energy. This one has to be lower energy than the 400 as well. That means it cannot be higher wavelength. It cannot be 200. It could be 600 or 800. And at this point, you could take kind of a guess, but the math isn't that bad. Energy is conserved, so the initial and final energies are the same. So the question is, the h nu of the 400 has to equal the sum of the h nus of the 1200 and whatever that other one is. And you can go through that math. It's a little bit of fractions here. Here I've multiplied by 3 top and bottom, so these both have denominator 1200. And then it's kind of obvious what this one has to be. 1 over 1200 plus 2 over 1200 would equal 3 over 1200. So this one is 2 over 1200. And that means its wavelength is 600. So there you go. Those of you that said 2, after I change those A, B, and C, are on course. Great. So let's go back to our diffraction and interference patterns here. So matter, the actual PowerPoint. Here, I'm going to end this one. It's not appended.
Oh, no, there should be more on my test.
But they're not right. So I actually have to go to 8. Right?
Maybe it's right there. Is that right?
Nope, it's the wrong 8. So I open a new one. I'll go to box and dive into box. Chat amongst yourself. So I'm going to go find lecture 8 here.
It's 920.
It's 920. I'll open it up, but yeah. It is 920. If you have some questions, you can ask some questions while I'm digging through here. I'm going to add a little alias so I don't have to dig through 8,000 folders on box to get to where I want to go. Are there any questions, guys?
Not yet.
There's quite a delay, so they might not have even heard me said. Are there any questions yet?
I also put it in the chat.
When will Prism be open to use?
There's a question coming in, when will Prism be open to use? And today is the answer. We'll get it set up identically today. You'll be able to start using it, and you'll start using it essentially tomorrow or even today if you are on top of it to use your to do your homework. So you'll stop doing your homework on B courses quizzes, and you'll start doing homework in the Prism software. It's the same. They're the same questions. They're just in a different. They're a different program. Still multiple choice. Still the same distributions. So we've talked about particles and waves, and we have the wave nature of particles now. So we talked about the particulate nature of waves. Can we go in the reverse and talk about the wave nature of particles? And I think you know we can, because many of you have had chemistry, and you probably even have heard, if you haven't, that there's quantum mechanics, wave mechanics, particles behave as waves. And it is true, they do, the very tiny ones. And if they do, we should be able to do a diffraction pattern on matter. So we should be able to take a beam of electrons now. And the beam of electrons will create a diffraction pattern. They actually do this. So electrons interfere with each other as if they were waves. This is a manifestly wave-like result. But it happened when I shot particles through a diffraction interference type experiment. Turns out it's not through slits. You do it in a crystal, because you got to get those slits so darn for this electron diffraction to happen. You have to use the spacings of layers of a crystal, layers of a solid, to get your spacing small enough between the slits. And indeed, that does happen. And again, we are going to take the intensity of the peak to be the probability of the particle striking at different places on the screen. So now it is kind of a real probability. Intensity proportional to probability. Amplitude squared is equal to, or is a measure of the probability. And this thing looks like a wave function. So it's not a formal wave function, as we'll see as we go forward. It looks like the wave function that written down before. Here's y of x equals sine of x. We've written that one down before. And we have written the form of the wave function. And here's the square of the wave function, square of the amplitude. So we could make the connection even here in our wave-like property, that there's some kind of probability-like property involved in the amplitude squared. So it's kind of funny to think about if the particle is behaving like a wave, and now we kind of know it does. So here's a particle behaving like a wave. We're saying that the amplitude square is going to be something like the probability of the particle being there. And you already see, interestingly, well, if I behave like a wave and I'm a particle, I can't be everywhere. Just like here, the intensity particles are hitting here. That's a dark spot. Lots of particles hitting here, and it goes light, dark, just like your interference pattern from the laser. And you see that same kind of, here it's the sum of lots of waves, there's just one wave, but you see that same kind of behavior here. A place where there aren't particles. So that's a little odd. This is a little odd. And this gets spookier and spookier and spookier. You can dive into this, and as Jiho would say, you're going to go down a rabbit hole of physics that you don't want to go down. Actually, you do want to go down. It's crazy cool. You're never going to understand it all the way. But and I don't say that because you guys aren't smart enough. The smartest people in the world are trying to figure out what's the mathematics that explains this phenomena. And here's the weird part they're trying to explain. You could understand if particles were going through both slits and could interfere with each other. But you can take this electron beam down to such low intensity that it's one electron at a time. And even if one electron at a time goes through, they still don't hit here, and they hit here. So there's no other electron, there's no other wave to interfere with. But it still gives you an interference pattern. That should give you the willies. Maybe just this gave you the willies. If that didn't, then the fact that I go one at a time and still get interference, if that doesn't give you the willies, you're not listening. Or you're willy resistant. Is that such a thing? Really resistant. Correct myself. So wave functions, probabilities of the square of the wave function, we'll talk about that. So just to summarize, just like I did earlier, so now it's the wave nature of matter instead of the particulate nature of light. And what we see are, we have these things called wave functions, and they have a lambda associated with them. Well, can we do this association? Can we say that that lambda is related to the momentum of the particle? And now it is a real particle. So it is matter. So can I say, well, this is a particle with real momentum, real mass, times its velocity. Is there this relationship between some kind of wavelength that it has? And we can measure the wavelength, because we can do that diffraction and interference pattern. And you know the spacing tells us what the wavelength is. We know the spacing of the slits, we know the spacing on the screen. We can calculate the wavelength. Does that correspond to the momentum of the particle as it entered the system? And it turns out, yes, it does. So all this wave-particle relationship that we got for light applies to matter. Matter is indeed a wave. It's wave. So we'll just summarize the rest of that. We're going to get this same duality in our waves of matter as opposed to our waves in electromagnetic radiation. So we'll stop there. We will get, we'll send out some announcements. Please read the announcements that you get via email. They're also stored on B courses. You'll get information about PRISM. I'll talk about it tomorrow. You'll get information about the exam coming up, and we'll just keep you abreast of everything that's happening on the email announcements and the announcements listed on B courses. Have a good day, if you can, after hearing all that, and we'll see you tomorrow. Am I clear?
Ending.